So it is peak value of the current times sines of angular frequency of the current multiplied by time, the instant at which we calculate the current, plus initial phase of the current. Now, in order to relate this to voltage, I would have to calculate the derivative of it and multiply by inductance. How did I know that? How did I know that I have to take the derivative and multiply by inductance? Because we are talking about inductor, correct? So it's from the definition of inductor and inductance. All right, let's now calculate the derivative of this expression. Here we have a constant. I can take it in front. And then derivative of a composite function. External function is the sinusoidal function. Internal function is a linear function. So which rule are we going to use in order to differentiate this function then? Chain rule, correct. All right. So I have this peak value from here. Well, omega came from the derivative of the internal function. Derivative of sine function is cosine function. All right. I almost have voltage written as a sine function, except that it isn't sine function but cosine function. I now have to convert cosine into sine. And it's easy actually to do because cosine and sine function are just shifted. So I can write down that cosine of a certain argument is equal to the sine of the same argument plus pi over 2. Now I wrote voltage as a sinusoidal function of time. Yeah, I have a certain number times sine of angular frequency times t plus a certain number. Now, looking at this expression, how big is the peak value? Or how is it related to peak value? Well, I mean, in terms of the quantities which we have on the screen. Yes, Bill? Right, which means omega L times Im. This entire expression here is the peak value of the voltage. This is peak value of the current. So what is impedance of the inductor? How much? Angular frequency, not velocity. Angular frequency multiplied by inductance, correct, yeah, because if I divide this expression, which is peak value of the voltage, by the peak value of the current, I will get omega L. So omega L is the impedance of the inductor at frequency omega. Note actually a major difference between impedance of an inductor and impedance of a resistor. Impedance of a resistor was the same for at all frequencies. Impedance of an inductor varies. So if current oscillates slowly, impedance of the inductor is high or low? Low, correct. And the higher the frequency, the higher the impedance of the inductor. All right, let's now look for the phase angle. What will be initial phase? Phase angle produced by the inductor. Now, what is phase angle, by the way? What is it? So that we know what is what of what. First of all, phase angle is not an angle. We can interpret it as an angle somewhere. Where? Not at the instant. On the phasor diagram. But if we look at these two, there is no angle anywhere here. Over here, for example, I can recognize what is the phase angle between voltage and current. By definition, what is phase angle? It is just a difference between phase of the voltage and phase of the current. You can also think about that it's a difference between the initial phase of the voltage and initial phase of the current. At any instant, is going to have the same value. So how about if we look at this? Let's say I consider this instant. What is the phase of the voltage? Voltage is the blue, represented by the blue plot. What is the phase of the voltage at instant 0 here? Oscar? It isn't negative pi over 2. It's just pi over 2, right? The value is 1. I mean, the highest value, right? So it means the phase, the argument of this sine function at t equals 0 is pi over 2. All right, so phase, and let's remember that. So phase of the voltage at instant 0 is pi over 2, which is actually the initial phase of the voltage for this for these two plots. What is the phase of the current at this instant? 0, correct. Can we subtract those two? And which we should subtract from which? From the phase of the voltage, we have to subtract phase of the current, which means that from pi over 2, we have to subtract 0, and the result is going to be pi over 2, right? So if I look at these two plots, phase angle is pi over 2. Let's now choose another instant. How about this instant? What is the phase of voltage at this instant? How much? 0, correct. And this one? Negative pi over 2. 0 minus negative pi over 2 gives us pi over 2 again. Right. So no matter what, we always get pi over 2. And if we take a look over here, this number over here is the initial phase of the voltage. So initial phase of the voltage is equal to initial phase of the current plus pi over 2. So if I look at this expression, what is the phase angle? No, pi over 2. Yeah, because from this number or from this number, I have to subtract either this number or this number. So no matter what, I will get pi over 2. So in an inductor, impedance is equal to angular frequency multiplied by impedance of the inductor, and the phase angle is always pi over 2, which means if it is pi over 2, we say that the voltage leads the current by phase pi over 2, or we say also that current lags behind voltage by pi over 2. Phase of the voltage always happens a little bit earlier than phase of the current. Look at that. At this instant, voltage has phase pi over 2. Well, we have to wait 1/4 of a cycle for the current to get to phase pi over 2. At this instant, phase of the voltage is pi. We need to wait 1/4 of a cycle for the current to get phase pi. Let's now take a look at the phasors. Oh, average power delivered to an inductor. Well, average power delivered to an element depends on the root mean square value of the current flowing through the element and potential difference across the element times cosine of the phase angle. Cosine of pi over 2 is 0, so on average, inductor does not consume power. It is that in certain fragment, well, actually we can take a look at this. Let's say at this instant, how much power is delivered to an inductor? 0. Now in this interval, power delivered to the inductor is positive, negative, or 0? Positive, yeah, because both current and voltage are positive. How about this interval? negative. Current is positive, voltage is negative. So here the inductor delivers power to the circuit. Now, here is again positive when both electrical quantities are negative. And negative and positive. So in an inductor, we deliver power, take it away, deliver power, take it away. Let's take a look now at the phasors. So we start again with the relationship between voltage and current for an inductor. And I recognize that here I have that voltage is imaginary part of the complex voltage, and current is imaginary part of the complex current. And since when we calculate derivative of a complex number, we separately calculate derivative of the real part and imaginary part. And since L is a real number, I can recognize that this expression is imaginary part of such a product. So I can now relate complex voltage and complex current by the same relationship as voltage and current are related. All right, and let's now say that I take current, this complex current. I will write complex current as a complex amplitude of the current multiplied by e to I angular frequency times time. Well, this is a certain constant. I can take it in front. Derivative of exponential function, this is still a composite function. External function is exponential. Internal function is linear. And the coefficient in front of the variable is I omega. So the derivative of the internal function will be just I omega. And exponential function has this property that when you calculate the derivative of exponential function, you get again exponential function. So it is just, so calculating derivative of exponential function is equivalent to multiplying the function by a certain constant. Well, that constant here is I omega. All right, so this way I was able to relate complex voltage with complex current. In general, proportionality coefficient. The proportionality coefficient between complex current and complex voltage is called, you will have to go again through all, to repeat the relations. So what relates impedance, root mean square value of the voltage with root mean square value of the current? Impedance, correct. What relates peak value of the voltage with peak value of the current? Impedance. What relates current with voltage? Nothing. Good. What relates complex voltage with complex current? Complex impedance. Correct. All right. So the proportionality over here, Adam is right, is indeed complex impedance. I omega L is the complex impedance of the inductor. All right. On the previous slide, we found actually what is impedance. Can we verify that everything agrees? Yeah, because how from this number find impedance? What do we have to do with complex impedance in order to absolute value? Correct. You're absolutely right. Okay. So when we calculate absolute value, it is equal to, of a product, it's equal to product of absolute values. What's absolute value of I? 1. All right. Now, omega is a positive number, absolute value and real. So absolute value of omega is omega. Absolute value of L is L. So, oops. This is where we would mark the number. And impedance is indeed angular frequency times